Hello, ladies and gentlemen. Let's talk about gliders in flight, stability, and straight and level flight. This is important to understand for the successful build of a glider. So what we want to see happen when we have a glider flying is it should be flying level and flat. It shouldn't be climbing. It shouldn't be falling. It should be balanced and stable in flight. So one thing we have to keep in mind is that gliders don't have an engine. They can go out into the wide world and find what are called thermals. This is where patches of warm air are rising. And ideally what they would do is get in that thermal and ride the rising air up to a higher elevation and then glide down from there. Again, we are going to get the maximum distance from a glider if it's flying straight and level. This is a reminder that we have three axes of motion. We have roll, and that's the wings tilting left and right. We have pitch, that's the nose pointing up or pointing down. And we have yaw, and that is like a rotation, a flat rotation looking down on the plane. Kind of like this. So we can see from above the plane would point to the left or to the right. And there's roll. There's pitch. What we want to see in flight is like this first example. We want to see a flight that is in equilibrium where it's not climbing, it's not falling, it's flying along straight and level. Before I talk about B, let's talk about C. In part C, it's neutral and it's static and it's stable. So in this case, we've got a disturbance and the plane is at this strange angle, but it's continuing to fly in a straight line. This is really odd. It does happen, but it's not a desired thing. We want this plane to correct itself and return to flat, stable flight. And the least desirable of all is statically unstable. And that's where the airplane's flying along. It has a disturbance, and no matter what the pilot does, they can't get the airplane back under control. Those are the kinds of stability we needed to talk about. Okay, good. Moving on. And here's some more of those, and it's just variations to the same thing. What we want to see is, like if it has a disturbance, it oscillates a little bit and returns to straight flight. And then what can happen sometimes is it oscillates and it continues to oscillate as the aircraft flies. Or the worst scenario is when it's oscillating and it's getting worse and worse and worse until the plane crashes. So if we're talking about lateral stability, we're talking about roll, and we want the airplane to behave when we enter a roll. Another idea is the idea of dihedral, and that's where the wings are tilted up a little bit, as you can see in this diagram, and that adds to stability. So what happens is if you are flying straight and level, you have uniform lift on both wings and the weight pulling down at the bottom. If you tilt, what happens is the surface area of the left wing in this case is larger and the surface area of the right wing is reduced because of the increased angle, and that increases the lift on the left side and reduces the lift on the right side so that you end up with higher lift, lower lift, and that causes it to roll back to stable flight. There are a wide variety of dihedrals. You can have no dihedral, which is just a flat wing. You can have a straight dihedral where the angle occurs at the fuselage, and you can have tip dihedral where partially down the wing you can have it tilt up. A lot of gliders that you see that are large use the tip dihedral. And you can have a polyhedral, which takes advantage of both types of dihedral, both straight and tip. Let's talk about movement in yaw. One of the things we need to think about is the keel effect, and this diagram really doesn't help because it just says, hey, look at this arrow and look at this airplane. So an arrow flies because it has drag at the back and a heavy pointy nose, and it flies like in a straight line where the tail is always behind the nose. What can happen with an aircraft is if you have a crosswind, it acts just like that arrow. So if you have a wind that's going at an angle to the length of the fuselage will act as a weather vane, or it's called the keel effect, where it will try to align the airplane with the wind it's flying into. You can see this when aircraft are landing in heavy crosswinds. You'll see that the plane is actually landing at an angle even though it's flying straight. All right, so let's look at directional stability. If you look at these two aircraft, they're both B-17s. One is the B-17C and the other one is the B-17E. If you notice the rudder or the vertical stabilizer on this aircraft, that the one at the top has a very small tail compared to the one at the bottom. And the problem with this aircraft was that in the B-17C, with the small vertical stabilizer, the aircraft was extremely difficult to control because it didn't have enough surface area there to keep the heavy front of the plane in line. So what they did is they added this enormous tail, and that made it where they had better control of the aircraft in flight. Let's talk about movement and pitch. We're talking about the nose pointing up and the nose pointing down. So there is something, and this is something we will learn about, or you learned about in the airfoil simulation. There is a point where the wing stops functioning as a wing. When you have turbulence occurring on the top of the wing, you lose lift. Okay, and if you look at this, this is showing the angle of attack, and as that angle of attack increases, your lift increases until it gets to that critical angle, and after that, you have turbulence over the wing, and it loses its ability to produce lift, and that's when your aircraft will stall. Another thing, we've also done the center of gravity and balancing the aircraft. So what we want is the center of lift over the center of gravity, and that's going to maximize our stability in our aircraft. In the glider designs, we have some that are designed such that the center of lift and the center of gravity are not in the same place, and as a result, they are going to have a tendency to be unstable and very hard to trim out and control. So the idea of this is, think about a teeter-totter. If it's balanced, it's going to be easy to control. If you have a lot of weight moved forward, then the nose of the plane is going to try to turn down, and you're going to have to continually have your elevator pointed up so that it can try to lift the nose. There is a point where you get outside of what you can control with the elevator for that. And if you move it back behind the center of gravity, it's the same thing. If you have a tail-heavy plane, it's always going to be trying to point up, and it's going to be hard to force the nose to go down. So that's the weight and balance. So again, you have an optimum place that you want that center of gravity to be, and it needs to be about where the center of lift is. And that's all I have for now. So what I would like you to do is think about how these apply to your glider flight. Thank you for watching.